Okay, this is an Effusion demo. We've got a 500 Erlenmeyer flask with some water in it. Nothing special
Porous
there.
cup.
It's got essentially thousands, millions of little tiny holes in it. We'll get to that in just a moment. We've got a container that's going to hold our hydrogen gas. Hydrogen gas is currently inside of here. This is two glass tubing, 2-hole rubber stopper, 2 glass tubings. This glass tubing comes through the stopper and just kind of ends, and it's supported by a wooden dowel rod, just kind of velcroed in place to give it some extra strength for the stuff that's going to be hanging on the top. Then this will go all the way to the bottom of the flask and then comes up, takes a right-hand turn, and then angles up. I take the porous cup, and on this stopper that's attached to the top, I gently, because it is just a ceramic container, I gently twist that to tighten it. So we imagine the air molecules effusing out at the same rate that the air molecules are effusing in. As a result, the pressure in here stays the same, the water level stays the same, nothing special happens just yet. You might say it's empty, but really it's filled with air. And so when I put this over the top, there's still air effusing in and out at the same rate, so there's no change in the water level that's going to occur. What we're going to do next, though, is add hydrogen to this container. So I'm going to take this out. Hydrogen is less dense than air, so we fill it upside down. And now this we're going to bring up to the top and up and over. I can get a little bit more a more satisfactory reaction to this if I fill this with hydrogen gas from my cylinder. But watch as I take the container away from the porous cup what happens down here. Okay, so think about that for a moment. I'm going to go fill this with hydrogen gas from the tap. Alright, here we go. I've got hydrogen gas now from the cylinder directly. Let's try it again. There we go. It's a little bit better result there. The hydrogen being more concentrated on the outside was effusing in faster than the air was effusing out. Hydrogen has a smaller mass. Therefore, it's got a greater kinetic energy, a greater velocity, the same kinetic energy, they're at the same temperature. It has a greater velocity, therefore it has more opportunity to effuse through those holes. So more hydrogen molecules move in than air molecules move out. That means more gas molecules are inside, creating a greater pressure on the surface, greater than air pressure, which is pushing on this side. And so the pressure inside the porous cup cylinder headspace is greater, and it pushes the liquid out. At this point, the rate of hydrogen and air on the inside of the cup effusing out is equal to the rate of hydrogen and air molecules effusing in. So when I take this away, there will no longer be hydrogen molecules on the outside effusing in, so the hydrogen molecules on the inside effusing out will lower the pressure. Let's take a look at what happens there. And now the now the pressure here is less, which means air pressure is greater, and it's blowing bubbles into the bottom right there. I'm going to do that one more time for good measure. Okay, more hydrogen gas. I think we'll also try helium gas. I've got helium gas over there as well, so I'm going to do that next. Okay, I got some helium gas. Here we go. Helium gas works also, but notice it's not quite the same effect.